or students, can you just type in the chat box so I get an understanding of how many of you here are adults and how many of you here are students? Um, you can type. Or I would like everyone to type so that I get an understanding. So I see a parent, student. I see two, three, four responses. Student. A lot of you are students. Okay. Some parents. Yeah, type. I can wait for a minute for you all to type. Yeah. Okay, student. Okay, I assume there are some parents and most of you are students, but nevertheless, all of us, assuming you guys are between the standard, fifth standard and 10th standard, or some of you are even older. So I'm sure you have subject science, all of you, physics, chemistry, or whatever subjects, and I'm sure the parents also have been through this system once upon a time. So you would have also remember these subjects to an extent. So one of the things that normally happens in our science textbooks or the way we are taught science is that we are told about the facts, like for example, what is light, or what is gravity, or what is anything. For example, evolution. There are so many things that we're taught in the textbooks at a superficial value. We are never taught about the history of how something came into existence or how our understanding has improved. So it is natural that we take a lot of these things for granted. So when we talk about light, we take things that are around us for granted because we do not know or do not value it, because we do not understand the rich history that has gone in the past to lead us to the moment that we are right now here today, that we are talking to each other. Okay, so more on that later. I'll conclude the session with more of these like understandings. But before that, let me get into the topic straight. I'm sharing the screen. Let me know if you're able to see it. Your is it visible? It
Not yet.
okay. It is not visible to me also.
Yeah, the sharing has started. It's now visible, the story of light.
Okay, great. Okay, this story is about. By the way, I should let you know a few things. If you have any questions, you can type in the chat box. But I would prefer to take the questions at the end of the session so that I'm not interrupted. But if you have questions, please do type in the chat box, and Kavyaka will read it out to me then and there. But I would like you to listen first to the entire story, and then you can ask your questions. Okay. Okay, so now this is a story about how our understanding of light has changed, or rather, I would not use the word change, but evolved from 2000 years ago, or even before that, so from 2500 to 3000 years ago to the moment we are today. So, how was their understanding of light? So, not just you and me, even in the past, people have always been excited about things around them. So when I say things around them, they are curious about the nature around them. They're curious about how plants grow. They're curious about how sun rises or what is the sun made up of. They're curious about everything. So one of the things naturally for them to be curious about is the light, because light is something that is all around you. You see things. You see things that in the morning you see things because the sun rises, it lifts up the entire world, one half of the world at least. So you see things. While during the night, you're not able to see. Of course, if not for the moon, you would not be able to see anything at all in the night if you don't have any source of light. So people have always been curious about what is this light? What is that the sun has got something that nighttime it is absent? When what I'm not talking about today. Today, of course, you know a lot more about the light because you have learned them the textbooks or the teachers have taught you. But back then, about 3,000 years ago or 10,000 years ago, when there were no understanding about anything about light, people were curious. People did not know what was light. So this story is a culmination of like what began. The curiosity began like several thousand years ago, and how it led to one event after the other, each adding on to a little more understanding of light to what we have today. So that is this about, and let's get into it. Are you able to see the slide? Second slide yet? Uh,
No,
why I'm moving to a second slide, but it's not changing. Let me see. Okay. Still not see visible, right,
No,
Kavya?
no, no, no.
Okay, let me share again. Sorry, I think I have, oh, two slides I have repeated. That's why it looked like it didn't move. Sorry about that. Okay. Now, right? You can see it, right?
Slowly. Yeah.
Yes. So I'm sure that there have been people before Empedocles as well who have been curious about light, but we all rely on the historical records. Based on the records that we have, looking back, it is very difficult to look back 2,500 years ago, 3,000 years ago, because we have to collect evidences, we have to collect the scriptures or people that people talk about different things. So we'll have to be reasonably sure about who said what. So these are some of the evidences we've been able to gather over the past hundreds of years about the history of what has gone through in understanding of light. So we have this Empedocles. We really do not know if Empedocles was one person or had the same name or what he looked like, but we have some evidences referring to his name. And he lived around 500 BC, which is about 2,500 years ago. So he was of the idea. I mean, when I say he, in his era, in his time, so he proposed the idea like the entire Earth was, entire world, or sorry, the entire universe rather, was made up of earth, fire, water, air. It's not just Empedocles. People across various civilizations, Indian civilization or Chinese civilization, different civilizations, they had this idea that everything it was made up of earth, fire, water, air. Like I'm sure the space has been included right now. So five elements of nature or four elements of nature. That's how they looked at it. So Empedocles was of the idea that the eye, the human eye, he considered it to be one of the most beautiful things in the entire world. The human eye is able to see and appreciate a lot of beauty. So he envisioned the eye to be made up of these four elements like earth, fire, water, and air combined to come up with this creation of eye, and it was lit by the Greek goddess of Aphrodite. So it was what made the vision possible. So people were concerned about the vision. How are we able to see things? How are humans able to see the things around them? So that was the curiosity that gripped the people back then. So they came up with this idea of earth, fire, water, air being combined to make the eye, and it was lit by the goddess and gods to make the vision possible. So that was the earliest, record of people trying to understand light. And then we had Euclid and Ptolemy. How many of you have heard of these words, Euclid and Ptolemy? Any of you heard of these names, Euclid and Ptolemy? I'm glad one of you is saying geometry. Yes, Euclid is most commonly associated with the word geometry. Euclid's geometry, you call it. So he is also called as the father of geometry. So if you hate mathematics right now in your school, where you're asked to solve, construct triangles, construct rectangles, or draw perpendicular bisectors or angular bisectors. You have so many things about geometry in your textbooks, right? So Euclid can be attributed as the father of the geometry, a 2D geometry at least. So way back in 300 BC. In fact, I have the Euclid's books, 13 Elements. It's also known as 13 Elements. So what we know about Euclid is about geometry, normally associated. But what we do not know about him is that he also thought about light. He also wrote about light. He also has his own understanding of how light is there, what is the nature of light, and things like that. Euclid and Ptolemy lived around the same time, like 300 BC to 200 BC. So what both of them proposed, this, the light travels in a straight line, which is true even today. Light does travel in a straight line. So that was their proposal way back in 300 BC, that light travels in a straight line. And also Euclid was able to come up with the laws of reflection. So he was able to come up with the laws of reflection, like when light falls on an object, it reflects. He was able to be, since he was already good in geometry, he understood geometry very well. He was able to study light pretty easily. Like imagine light to be traveling in a straight line, and what angle it falls on an object, and what angle should it be reflected. He was able to understand these things better because he was good at geometry already. So one difference though, right now, one of the ideas that they had, both Euclid and Ptolemy had, was that nature of light, where is the light coming from? So both of them thought that light was coming out from the eye. the eye was responsible, like, is, imagine it to be like this: the eye was emitting a sort of a light beam, and it falls on an object and it comes back to the eye. It's like Superman, for example. He sends out some light and he's able to scan stuff, right? Superman, if you're any of your like Marvel or DC fans, you know Superman is able to scan stuff. How is he able to scan stuff? Because he is able to emit sort of an X-ray from his eye, and he is able to scan things. So way back, Euclid and Ptolemy imagined a human eye to be emitting something, like it's emitting something and it's able to scan things, it's able to see things, because the emitted light falls on the object, hits it and comes back, reflects off the surface of the object and comes back to the eye. So that was the idea back then. So both Euclid and Ptolemy proposed this idea. And there was one other question that Euclid was faced with. For example, when you look up at the night sky, you look at the stars. So back then, even Ptolemy was an astronomer. He was a very famous astronomer. So they all knew the stars. They did not know how far the stars were. None of our ancient people were able to calculate how far the stars were, but they knew the stars were far away. That much they were able to tell, but they did not have any technique to tell how far away, like how many light years away they were. But the very fact that they are very far away, still we are able to see them. For example, when you close your eye, the stars disappear from your vision. The moment you open your eye, the stars become visible. It's like almost in an instant. The stars are very far away, but still, the moment you open your eye, you are able to see the star. So Euclid was faced with this question. Then Euclid came up with an answer, like, it should not be a problem, because if the light traveled at infinite speed, light traveled instantaneously. Like the moment you open your eye, the light from your eye travels at infinite speed, goes to the star and comes back from the star at infinite speed. So it's practically instant. The light will not take any time. It just goes and comes back to you as quickly as possible. It's like in an instant. So that was the proposal of Euclid. Like he said, light travels infinitely fast. Okay. And another thing that Ptolemy understood way back then is the refraction of light. When I say refraction, some of you have learned in the textbooks what refraction of light means. It is the bending of light. So even back then, people did not have lenses per se. Like right now, if you are wearing your spectacles or glasses, or if you have your magnifying glasses, you know that lenses are in everywhere, in use around us everywhere. But lenses were not made until after the 12th or 13th century. Okay, the lenses were not ground or grinded until 13th or 14th century. But still, Ptolemy and others understood of bending of light, because there are so many other natural sources which will require a bending of light explanation. For example, water. Water is a natural source that is available, but still water can bend lights. When you look at water, your image is distorted, your image appears shallow. If you put your stick into the water, I'm sure all of you have experienced this. Like if you put your spoon in a glass of water, the spoon bends, appears to be broken at the point of contact between the surface of water and above. So all these things were observed even back then, like during Ptolemy's time, because water was there. So they had to explain all these phenomenon. Why is the like stick appearing to be broken, or why is the of course, there were a lot of other optical illusions as well. For example, mirage. On a very hot sunny day on the floor, you will see like illusions of water, so I'm sure you've experienced this when you're driving on a highway. So all those things demanded explanation from these people, and that is when Ptolemy talked about refraction of light. The light is probably bending when it goes through different mediums. So that talked about. And of course, there are so many other things Ptolemy was famous about. One of the things was the geocentric model of the world, of the solar system, like placing Earth at the center of our solar system. And he said everything moves around the Earth, like the sun, the other planets, everything moves around the Earth, Earth being in a fixed place. So these were the earliest ideas of light. And there are a few other theories. For example, there was this guy named Lucretius, and there were some ancient Indian philosophies and other civilizations philosophies, like for example, where they thought of light to be some particles, like small fire particles. So the most common thing that people back then associated light to was fire. Okay, The most common thing. So whenever they look at fire, they immediately imagine of light. So fire is nothing but light for them. They don't. What is the nature of fire? They understood it only in terms of light. So if there is fire, then it is emitting light. So they taught light to be emitted by fire. It is particles emitted by fire. Okay, you can think of them as atoms also. Like they're nothing but atoms emitted by fire. Okay, even sun, they thought of it to be fire, and they're emitting particles. The sun is emitting fire particles. It is coming and hitting us, and that is why we're able to see it. So those are the kind of things, few other theories that floated around in the first century AD, or the first century BC. Around that time, these were few ideas that were floating about light. And then for a long time, the understanding of light did not improve much. Then they came this person called Alhazen. Okay, who lived at about 965 AD to 1040 AD, nearly 1,000 years after the Ptolemy and Euclid's time, a little more than that as well. So he came up with an experiment called two lantern experiment. So he went to a dark room. He was inside a dark room where there were two small openings. Okay, two small openings, and behind these openings were two lanterns of light. Okay, and he observed inside the room what was happening. So he observed that what is the natural expectation. Wherever there is hole, the light will enter the hole, and there is going to be light inside the dark room at that particular spot, right in front of the lanterns. All the other spot of the dark room is going to be dark. Only those two spots are going to be bright. So now he blocked one of the holes, and when he blocked the hole, what is natural to expect? The spot where on the wall inside the dark room where there was light, now there will not be any light. The moment he opens the hole, the light is there. The moment he closes the hole, the light is not there. So now, look, it is a very simple experiment. Look, come on, from you guys might think, is this an experiment? It's so simple an experiment that I can do it now, and I've always known this. So the reason that you claim that you've always known this, because you've been taught from your childhood that this is the nature of light. Okay, but back then, people did not think about this way. So back then, this was a very big experiment. Okay, so when they did this, they observed, okay, when the hole is closed, the light is not there. When the hole is open, a light is there. So now this means the light has nothing to do with coming from our eye. If it were coming from our eye, the light should be visible anytime. Whether we open or close, the light should be visible. The spot should be visible. But now, the very reason that the opening and closing of the holes is giving us light or not, defines or proves that the light is coming from the lantern. The light is coming from the lantern itself, not from the eye. That is to say, the lantern is visible not because of the light emitted by our eye falling on it and coming back, but light emitted by the lantern itself. It has nothing to do with the human eye. Okay, so now this was a very great revelation back then. So it proves whom wrong. Whom did it prove wrong? Whose idea did it prove wrong? I remember I gave you two names earlier. Uh, they were of the other idea. Euclid and Ptolemy. Euclid and Ptolemy. So this was the very first time that it was conclusively proven that people call it extra mission theory. Extra mission theory is like light coming from our eye, falling on an object and coming back. That theory was completely proven wrong by Alhazen, and he went on to do a lot of work, but I'm talking about one particular experiment that he did. So now there was another problem with Alhazen. So though he thought that, though he proved or rather proposed that the light comes from the source itself, like for example lantern has a lot of points of light, right? Lantern is not just one point, it is made up of lot of points of light. So now all the points of light coming from the lantern will fall on the human eye, all the points of eye, right? So look, our eye is not one single point, right? It is like it has got some size, like it's probably 0.7 to 1 centimeter across, or a little more than that. It has got certain dimensions like length and breadth, or if you think of it as a circle, you can think of some radius or diameter of this eye. So now the light coming from an object, it will not fall in one point, right? I mean, that was what Alhazen thought. Alhazen thought the light from all the points on the object will fall at every point on the eye. Every single point of the light will fall on every single point of the eye. So now he was confused. Then if that is the case, how is the eye able to see the image? Shouldn't it be chaotic? Shouldn't it be confusing? Because it is falling on every point of the eye. So how is my eye able to construct a proper image of what I am seeing? Or rather, the problem of coherent image was still unresolved. So he was still not able to come up with an explanation for that. Of course, later we know why that happens, but we'll come to that later. He was also the first person who experimented with the idea of a pinhole camera. I'm sure all of you in your textbooks learn about pinhole cameras, how images that you see through a pinhole camera is inverted. So Alhazen was able to come up with design a pinhole camera. Of course, later it was, I think, done better by Kepler or few other scientists who made a better version of pinhole camera. But he understood the idea of pinhole camera and constructed the first set of pinhole camera. So this again was the very first. So now, till this, do you have any questions? Do you? I'm going into the second phase of my session. Do you have any questions until now? You can ask. Then I'll move on to the next. You can type in if you have. Okay, good. One person says no. Okay, good. So I have it to. Dikshita, I'll come to that. I'll come to the aspect of speed of light later. Eventually, I will cover that in the topic. Upcoming slides, I will cover that. Okay. So now, until this time, like Alhazen or even people after that, until about 15th or 16th centuries, people were more concerned about human vision. Okay, people were like, how are humans able to see? They did not think about light itself. The light was thought from the idea of how humans are able to see. It did not go beyond that. It was restricted to, if you want to study light, people studied light because they wanted to understand the vision of humans. Okay, how are humans able to see? That's all. So now, something happened in 1543 or early 16th century. Okay, we call it the scientific revolution. Okay, when I say scientific revolution, you might wonder, like, is it about one theory that came about, or what do you even mean by scientific revolution? So the scientific revolution refers to the fact that the commonly held beliefs, okay, there were a lot of religions, a lot of philosophies, a lot of doctrines, a lot of things that cannot be questioned. Okay, so one of the problems even today with religions or other philosophies is they cannot question anything. Whatever is right, it was right. You have no rights to question them. It was all sacred. Okay, if you cannot question things that are sacred. If something was told in the holy books, or if something was told in the religious books, you are not supposed to question it, because that is true for a lifetime. But science is not like that. You can question it. So now that is when, in the early 16th century, people started questioning things. How can things that being written in the books can be right? Why can't we question? Why are we not allowed to question? So that is what I mean by scientific revolution. The ability to question things, to know things. That was a bold step. Okay. So until then, people were sort of scared. Even during this early 16th century, people were penalized. People were tortured. People were, even executed for speaking up against the religious scripts. But despite the fact, people went on and questioned. Okay, and that is a kind of a revolution I talked about. Okay, so now, of the many revolutions that the history has seen, the main revolution came about in 1543 when Nicholas Copernicus, I'm sure you've heard of his name, when he challenged one of the most commonly held ideas about the universe. I mean, back then people did not even know that there was something called as universe. Everything they thought about was Earth and the planets around them. They did not think of anything beyond it. Okay, so when he questioned the model of geocentric universe, a geocentric model of the universe or the solar system, wherein until that time there have been other people even before Nicholas Copernicus, Indians or other civilizations, where they questioned it. There is no doubt about that. Nicholas was the only person who questioned the idea of geocentrism. No, there were people even in Euclid's time, even in Ptolemy's time, in the contemporary civilizations like the Greek civilizations or Indian civilization, across civilizations, there would always have been people who questioned the idea of geocentric model. But it was in the time of Nicholas Copernicus where the evidences or like proper arguments, like valid points were starting being to put forward to counter the idea of geocentric model, and that is when the heliocentric model started gaining momentum. I'm not saying heliocentric model was proven in 1543, but the idea of Copernicus started gaining momentum. Okay, look, how can you prove something or not if you're living in a society where you can't even talk about whether geocentric model is right or wrong, or you're not even allowed to question? Do you think people will even dare to think about otherwise or other models? Because you will be executed, or you will be tried, or you will be penalized. So now in 1543, what Nicholas Copernicus was able to achieve was that he started gaining more popularity for his model. He started attracting more and more people, into looking at his heliocentric model more seriously. And also he, a lot of people that followed him, like Kepler and Newton, they came behind Galileo, for example. They started looking at his model seriously, and they started collecting evidences. Eventually, we went on to prove that Sun is the center of our solar system, and of course, today you know that. So that revolution started in 1543, where things were questioned. Now, of course, Copernicus, like Galileo and others, were threatened. Like that was there. Today, we don't have that threat of being ridiculed for questioning things, but back then it was a big deal. Okay, so now why am I talking even about the scientific revolution where I'm talking about light? What has this got to do with anything about light? Because of this scientific revolution, more and more people started investing in science. More and more people started questioning about the nature around them. They no longer were held hostage by the people who thought before them. They were no longer held by the minds or the philosophies or religious scripts. They were trying to break free and understand the nature as it is. They no longer held by this grip. So that is the reason why I'm talking about this, by the way. So even Ptolemy was of the idea of geocentric model. So for a long time, people believed in Ptolemy's model. Okay, but with Nicholas, people things started becoming more and more, in the direction of scientific revolution. So now in that line, after the scientific revolution began, we have a lot of important scientists who came about. One of them is Rene Descartes. Descartes, I'm not sure if you've heard of this name. If you are okay, I'll tell you about one thing that he was known for: Cartesian coordinate systems. It comes from his name, Cartes, Cartesian coordinate systems. If you are using graphs, for example, x-axis and y-axis, you use two numbers, right? X coordinates and y coordinates. The idea of a graph, or using a set of coordinates to point to designate a point, Cartesian plane or Cartesian coordinates, it came from him, Rene Descartes. He was the one to propose that, and he started using that in his understanding of the nature. So now Rene Descartes, as much as we know about him for the Cartesian coordinates or the graphs, we do not know about a fact that he also tried. He was also attempting to understand the nature of light and the laws of optics. He was not only concerned about human vision. Remember, I told you until that moment, people were only interested about what made humans see things. People were stuck with humans. People were always like obsessed with humans and humans. So whatever humans did, they wanted to understand. I'm not saying it's wrong, but they did not see beyond it. So Rene Descartes was also looking at beyond the human's vision. Can I understand light for what it is? Forget about whether humans are able to see or not. I want to understand what is light and lots of objects. What progress he made in terms of understanding light is a different story, but he attempted to understand light's nature, and he also wanted to discover what were the laws behind what the light obeyed, sort of the laws of optics. Okay, then you have I'm not going to talk into a very technical understanding of all these things. I'm just giving you a history of different people involved in improving our understanding of light. Okay, then you have Pierre de Fermat. Is probably one of the most important person who paved way or rather brought in one of the most fundamental understanding of the nature of light. Okay, a principle of least, I'm sorry, I did not type out the word time, a principle of least time. I'm not getting into what it means by principle of least time, but he came up with a law. He came up with a theory that talked about light takes the shortest time to reach another direction. From if light has to travel from point A to point B, it will take a route, or it will take a path that has the shortest time. So that is the essence of principle of least time. Of course, it's much more complex than that. It has got equations that you have to derive and so many different things. But in principle, he said to for the light to move from point A to point B, it will choose a path that has the least time, that will have the least time. Okay, so that was his idea. And if you are in your school 7th grade or 8th grade, you probably heard of Snell's law. Okay, the law of refraction, how light bends. So Snell was able to come up with these laws based purely on experimental observation. He used to shine the light through water, and he observed by what amount the light was able to bend. He passed light through different mediums. He understood. He recorded data like um, what is the angle at which the light falls, what is the angle at which the light bends after passing through water, for example, or after passing through glass, for example. So he made all these tabulations. He understood, he recorded numbers for all these materials and the angles, and then he came up with something called a Snell's law. He used something called he used trigonometry to come up with the Snell's law. I'm not getting into the law, but he came up with purely based on the observation of the experiments. He was able to come up with a law. But what Fermat was able to do was he was able to derive Snell's law without any experimental observation. He did not have access to the experiment where the light is passed through water and it is bending. He did not have any of those. He simply, if the light were to pass, obey the law of principle of least time, what will be the angle at which it will bend? Okay, so he purely used the idea of his principle of least time, and he was able to derive Snell's law. Okay, so this was his contribution to our understanding of light, like refraction. How is the light able to bend, or rather what happens when the light is bending, the light is slowing down, and different things related to that. Okay, again, you can also, by the way, I hope you are keeping track of the years. I'm slowly going up, like from the 3rd century, 5th century BC upwards. So right now we are in the early 17th century, like 1605 to 1675, where Pierre de Fermat was there doing his work. Then we have the next person. I'm sure this person requires absolutely no introduction. He's all over your books, or all over the place where you talk about science or talk about gravity. So one of the things that he's known for, most popularly known for, is gravity. Like I'm sure you know or remember the images of apple falling, and Newton looking at the apple, and his idea, his brain got triggered. Oh, the apple is falling. How is the apple falling? That is just a legend. Okay, nobody actually knows if actually Newton saw the apple fall down, and he got his idea from there. But it's just an interesting legend that you can relate to. Okay, I'm not saying that it is wrong or right, but it's an interesting story. But nobody actually knows for a fact that if actually Newton observed an apple and he got his idea from that. But we all know him for gravity. That is the point. Now, what we not know much about Newton is that Newton, like, he's a genius. Okay, like he's one of those people, like, there are so many other scientists. For example, I talked about Pierre de Fermat, Nicholas Copernicus, so many other scientists. But Newton is one of those people who stand out from the rest. Like he's like the best among the scientists. Or not the best, but he's the contributions, the kind of contributions he made to science, or the kind of thought process he was able to generate, is like he stands among, even all the other scientists look up to him. He's looked up like all the other scientists. He's at that level. So now it was not just gravity that Newton studied about. He studied about various aspects. Okay, there is not hardly any area of science that is not touched. Okay, and given that he's hardly not touched any other area, he also touched upon light. Light is something natural, because back then in his time, there are a lot of other people studying about light as well. So he was also curious. So what is this light? I need to understand light. What is this nature of light. So now he came up with his own theory. He came up with this theory that the light is made up of particles. Okay, so very similar to the ideas that were floating back in the early first century BC or first century AD, where people thought of fire atoms, like the atoms of fire are called the particles of fire. Now only difference is the Isaac Newton did not think that light was only coming from fire. He thought every object, the light, the particles were coming from every object, not just fire. Okay, the moment light falls on an object, the object will emit particles. Okay, he called them corpuscles. Okay, he called them corpuscles or corpuscles. I'm not sure about the pronunciation. So he thought of them as particles. Okay, that came out of an object, and he that was the idea that he had. And it is just one understanding of the light that he also came up with so many other aspects of understanding of light. For example, a color, like we talk about colors like red, violet, all the big like violet, indigo, orange, red, blue, all the colors. People before Newton thought that it was the nature of the object, like object itself has a color, like it is nothing to do with the light. Light is all plain. Light is one and the same. Depending on the object, the light will change the color. That was the understanding until Newton. uh, whatever the light is coming from the sun, it is all the same. There are no different colors in the sun. It is all like one thing that comes from the sun, but depending on the nature of the object where it falls on, the different lights are coming. So in a way, people thought the color is a property of the medium or the object that light falls upon. They did not attribute the color to the light itself. Now what Newton proposed, what no, it is not the property of the medium, but it is the property of the color, light itself. Light itself is composed of different colors. Light is not one thing, it has got different colors. So now I'm sure you know a very famous Newton's disk, or Newton's prism, where the light passes through a prism and it disperses into 7 colors of light. And he uses a second prism to combine all the 7 colors of rainbow to back into white light. So he was the first person to demonstrate that white light was made up of 7 different colors. So with that, he sealed the idea. He made it understandable that the light is made up of some different colors. Light is not just one thing, it is made up of different colors. Again, he came up with, and you also are aware of Newton's disk, where you have a disk where you draw all the 7 colors and you spin it fast enough, the disk appears white. Okay, it is a sort of a demonstration that all the 7 colors combine to give the effect of white color. So that was a major contribution. I would rather one of the most important contributions of Isaac Newton. And another interesting contribution as far as light is concerned about Isaac Newton is the telescope. So most of you, I'm sure you know what telescopes are. You can observe planets, you can observe stars or other gas clouds and nebulae and so many other things. Telescope opens up something that human eyes cannot even think of looking at. So it has opened up an entire thing, range of things that human eyes were limited by to look at. So now Newton is credited with properly building a reflecting telescope. So now look, why building a telescope is connected to light, because if you understood the nature of light, only if you understood how lights travel, you can even think of building a telescope that can, because at the end of the day, a reflecting telescope reflects the light, right? So the light has to reflect, converge to a point, and there has to be a lens that will magnify the image. So only if you understood light properly, you can come up with a proper design of a telescope. So that again, the reflecting telescope was a major contribution of Isaac Newton, and it also demonstrated his understanding of light, and it worked. So yes, now moving on to the next very interesting thing. This is one of the things that I like about science. It is not just the today that you have in your textbooks, light has so much of speed, light is this and that. Like, how did we come to know about this? So one of all the things in the history, one of the things that struck me was, I always had a doubt. How did even people know that light had speed? How can, like, of course, light, the moment in your room, the moment you turn off your light, the light turns off immediately. Like the moment you turn off your switch, the light is off. The moment you turn on your light, the light is on. Like, it looks like the light has no speed, or rather like Euclid and Ptolemy imagined way back several thousand years ago, light has infinite speed. Like light travels instantaneously. The moment you open the eye, the light from the star comes, or the light from your eye goes to the stars and comes. It's like people thought the light's speed was infinite. They did not even think of an idea that light has a speed. Okay, light has no speed. Now there comes this person, Oles Romer. Okay, in 1676 or 1679, around that time, 1676, I guess, where he again he was an astronomer, where he was observing several celestial objects. He was particularly interested. Galileo back in 15, no, not 1504, 1604, 1604. In that times itself, Galileo had a refracting telescope, a telescope made up of lenses. Where he had already Galileo observed the moons of Jupiter. A lot of other people were also interested in observing them. The moons of Jupiter moved around Jupiter. For example, if you keep observing Jupiter and its moons over different periods of time, like let's say 1 week later, not even 1 week later, they orbit the moon Jupiter in a matter of 10 to 12 hours, all the moons of Jupiter. So if you observe it like after a day or two, keep observing them, you see the moon, the position of the moons around Jupiter keeps changing. Okay, so they keep moving around Jupiter. Okay, now Oles Romer was interested in understanding just like how eclipses can happen on Earth, like when moon moves in front of the sun, between Earth and the sun, the shadow of the moon is cast on the Earth, giving us a solar eclipse. Similarly, from our point of view here on Earth, the moons of Jupiter can move in front of Jupiter, right? It's not necessary that it is always moving around Jupiter. From our point of view, one of the Jupiter's moon or more of Jupiter's moons can move right in front of the face of Jupiter, or also can go right behind Jupiter. So when it goes in front of Jupiter or behind Jupiter, the vision are looking at the moon is like the moon disappears from our view. For example, when the moon goes behind Jupiter, from our point of view, the moon disappears. And after some time, the moon is going to come back on the other side when it comes back into the view as it goes around Jupiter. So now the moons of Jupiter go behind and comes forward again. So Romer was interested in observing this how these Jupiter's moons move around the planet itself. Then he understood, like, during certain part of the year, when he observed the time it takes for the moon to go behind Jupiter and come back, it was different. If he, for example, he observes the Jupiter and its moons in January, he observes the Jupiter and its moons, let's say 6 months later, let's say in July or August. So now, when depending on what time of the year he was observing the Jupiters and moons, he found that the time taken for these moons to go around or when they would appear or reappear was different. The time between going behind the Jupiter and coming out of Jupiter appeared to be different. Sometimes it looked like the moon was coming out back into view sooner than expected. Sometimes it appeared that the moon appeared to come back into view later than expected. So there was always this time discrepancies. Why is it not same all the time? Is it the moon changing its speed all the time, or is it not moving around in a constant speed? Is it continuously changing? There are so many other things. Now Romer came to understand it is because the Earth is moving around the sun. The distance between Jupiter and Earth itself is continuously changing, right? Because sometimes the Earth is closer to Jupiter, sometimes Earth is far away from Jupiter. Because we are also moving around the sun, Jupiter is also moving around the sun, but we are moving much faster than Jupiter because we are closer to the sun. So now, if we are far away from the Jupiter, like we are moving far away from Jupiter, the light from the Jupiter's moons will take more time to reach us. It is not like a lot of time. It's probably in minutes, okay, or in seconds to minutes. That would be the difference in the time it takes. But still, because it will be probably in few seconds. I'm not sure of the exact time, but it should be in seconds to minutes, that range. So there was a discrepancy. So when he also observed when the Earth was closer to Jupiter. Now the light from the Jupiter's moon reached sooner. Okay, so now this made him realize that light has some speed. If light did not have speed, if light traveled at the same speed, like infinite speed, no matter whether you're observing it from far away from Jupiter or whether you're observing close from Jupiter, the time it takes for the Jupiter to go around, it should be the same. You should always be seeing the same. There should not be any time difference at all. But the very reason that the time varies depending on where you are, or where Earth is around the sun, is a very clear indication that the light has speed. That was the very first time in history that someone thought, oh, does not travel infinitely fast. It has a speed. So now, based on his own calculations, he was able to come up with a speed of roughly 2,20,000 kilometers per second. Look at the number again, 2,20,000 kilometers per second. Today we know the value is 2,99,000, or almost 3 lakh kilometers per 2,99,000 and so on kilometers per second. Yeah, because today we have more precise experiments that can have higher resolution, finer resolution, and finer experiments to determine a more correct exact value of speed of light. But back then in 1676, merely with an understanding of few trigonometric equations and the way the Jupiter's moons were moving around the Jupiter, to come up with something 2,20,000 kilometers per second was a phenomenal achievement. I mean, to me, when I read it for the first time, I was like, oh my goodness, this is just like unbelievable. Like this, it shows the what human minds can achieve. Only if we were not stuck to the old scriptures, like whatever they told us, only if we opened our minds to understand nature and be curious about it, will the world or the universe open us to give us what we want. So again, this was a major understanding. Now I will take another 10 minutes to finish. It's by 8 o'clock I should be able to finish. I'm just quickly going through it. So now from 1629 to 1695 AD, we have another person called Christian Huygens. Remember, until this moment, be it Isaac Newton or the people before him, even Alhazen, they were all thinking about light from the perspective of particles. That some particle was coming from an object. Even before that, Euclid thought that some particle was going out of our eye and coming back. So until then, people are thinking about light as particles. Okay, Christian Huygens was the first person who thought, what if light behaved like a wave? Okay, like a sound wave. Okay, like his idea came after Romer's understanding of the light having a speed, or light coming, how light coming from Jupiter's moons to our eyes. So he got his idea based on the observation from Olaus Romer, that he proposed the idea, what if light is a wave, like a longitudinal wave that moves forward and backward. Today we know light is not a longitudinal wave, we know it's a transverse waves. But back then Huygens proposed it to be a longitudinal wave, but he had this idea moving away from the long held idea of particle nature to a wave nature of light. Okay, so that was his. Again, I'm not getting into the details of his understanding of. You have Huygens' theory of propagation of light, where you draw concentric circles of light moving like ripples from point source of light. But I'm not getting into that. But I'm just giving you a history of who were there back then. Now we have, after that, we have Young's double slit experiment that happened in 1807 AD. Again, I'm not getting into what this experiment was. This I'll tell you quickly about this experiment. Okay, maybe I'll tell for another. This experiment basically probe gave the proof that Huygens' particle, wave nature of light was correct. Okay, so like the proposing hypothesis about a nature of something has to be validated by experiment. Okay, only then you will get it as a theory, where you know your hypotheses are proven by experimental results. So now Young's double slit experiment that happened in 1807 proved to be a definitive proof that light behaved like waves, and it was like a conclusive evidence back then to debunk the corpuscular theory of light that was proposed by Newton and others back then. So it shifted our understanding of light as particles to our understanding of light as waves. Okay, I'm just moving fast because I have to complete it in 10 minutes. Then you have this very famous name, Michael Faraday and Maxwell. Look, again, remember I told of Isaac Newton to be like this massive genius. I would put Faraday in that league of scientists, because he would the kind of contributions the course of science that followed from Michael Faraday's discoveries. So To make it short, he studied about the connection between electricity and magnetism. So that was his first uh, what do I say, entry into science. The reason he entered, or the motivation for him to enter into science, is the fact that people were back then trying to understand the relationship between electricity and magnetism. That was what got him into science and started being curious about what is going on. Then he eventually understand or go on to tell us that electricity and magnetism are connected. Electricity can produce magnetism, and magnetism can produce electricity, and so on and so forth. Several ideas about electromagnetism, and eventually we have Michael Faraday also proposed. He said. There is some sort of a wave that can emanate from electricity. He called them electromagnetic waves, and he not only proposed the idea of electromagnetic waves, he also said that light itself could be one of those electromagnetic waves that is coming as a consequence of electricity and magnetism. This was completely like, people had no clue. Like people, even before Faraday, people thought of electricity to be different, people thought of magnetism to be different, and people thought of light to be entirely different, not even connected. These three words were not connected in any sense. Electricity was separate, magnetism was separate, and light was separate. Now what Michael Faraday did in his initial phase was to connect the idea of electricity and magnetism, proving to be the same sides, to two different sides of the same coin. And later he went on to propose, look, light is also not different. Light is also a manifestation of the way electricity and magnetism behaves. It is also one of the consequences of how electricity and magnetism behaves, and that is what light is. And back then, Michael Faraday had no way of proving it, had no way of like proving to the people that light is an electromagnetic wave. It is a consequence of electricity and magnetism. But he had this intuition, he had this insight, what people call as insight. All great people have insight, all great scientists have insights. So Michael Faraday's insight was, electricity and magnetism is the cause of light. Like, this is a moment in history that you will have to remember, where three different, seemingly different concepts were tried to be stitched together. And now Maxwell comes along. Maxwell was very, very impressed by Michael Faraday. He was inspired by Michael Faraday, and he took on, among his several objectives in his life, he took on to prove Michael Faraday, or even at least take it further to see if what Michael Faraday proposed was actually true. Okay, let us try to understand if what Michael Faraday said about light being an electromagnetic wave was true. Then he went on to study about electromagnetic waves. He came up with equations. He came up with what we today call as Maxwell's field equations, Maxwell's equations of electromagnetism, okay, electromagnetic waves. So he came up with 4 equations. I'm not, of course, definitely talking about the equations is out of scope of this session, but according to one of his equations, okay, he discovered, it's purely out of the understanding of one of his equations. It's like one of his equations saying, one of his equations said that electricity and magnetism in a certain combination can produce electromagnetic waves. Okay, electricity and magnetism in certain combination can produce waves, and moreover, all those waves are going to travel at 3 lakh kilometers per second. Now this, I want all of you guys to please take a moment to sink this thought in. Michael Faraday or Maxwell had not experimented with the speed of light anywhere before. They had not heard of this number anywhere before, 3 lakh kilometers per second. But by purely taking forward Michael Faraday's proposal of light being an electromagnetic wave and studying it, and Maxwell, through one of his equations, it says that electricity and magnetism produces electromagnetic waves, and those waves travel at 3 lakh kilometers per second. Now, when James Clerk Maxwell looked at this number, he was immediately reminded of, I know of this number. I've heard of this number somewhere before. All of us have heard of this. This number is very, very familiar to us. And then they quickly recollect, oh, this is the speed of light. Because remember, Oles Romer in 1676, he came up with this number 2,20,000 kilometers per second. And after him, a lot of people did several other experiments to come up with a much exact value of speed of light. They had come up with the number 3 lakh kilometers per second, like in the 18th century itself. They knew the speed of light was 3 lakh kilometers per second way before Michael Faraday or Maxwell. But what was unexpected was some understanding about electromagnetic waves that had no connection to the experiment of light suddenly gives out a number 3 lakh kilometers per second. Now Maxwell is excited. Michael Faraday was all right, all along right. His intuition or insight about light being an electromagnetic was right. So luckily, Michael Faraday was still alive when Maxwell came up with this number. He goes to Michael Faraday. Look, I've proven you right. Michael Faraday was almost in his deathbed. Like he had only a couple of more years to live. So Maxwell goes to Michael Faraday. Look, I have proven your theory right. You are right. Like it's an electromagnetic wave, and look at the speed that it throws out. Look, these are the moments in science that tells us, like what we learn today in our science books has taken a lot of scientists and their hard works and their insights and intuitions to come up with something like this. And also Michael Faraday and Maxwell particularly, his equations also talked about light being a transverse wave, not longitudinal waves like Christian Huygens did. Okay. And again, I'm sure you've heard of this word, Heinrich Hertz. I'm sure those of you learning about frequency of light waves or sound waves, it is measured in hertz. So it is named after this scientist called Heinrich Hertz. In 1888 AD, he conducted an experiment that eventually actually proved the Maxwell's understanding of light, that light are transverse. There are several experiments that you can do to understand, prove that lights are transverse waves. For example, polarization of light. There are several experiments that you can actually do to prove that lights are transverse waves. So the Hertz did one such an experiment where he was able to prove the transverse nature of light. You see, right from 500 BC until 1888, so many things, our understanding of light has improved so much. Let me go on. I hardly have few minutes left, I guess. What is the time, by the way? It is. I have 3 more minutes before I can let you guys ask questions or end the session. So now we have another experiment, very famous experiment called Michelson and Morley experiment that happened between 1888 and 1900 AD, about 120 years ago from today, 120 or 130 years ago from today. So I'll very quickly tell you what this is. Uh, since people were coming to an idea that light was a wave, and there were a lot of experiments that proved that light was a wave, like Maxwell, light from Maxwell to Huygens to Henry's Hertz to a lot of other Young's double slit experiment. So many experiments that were done back then to prove that light was a wave. Now the question was, if light was a wave, it required a medium to travel. For example, sound waves require air to travel. Without air, sound waves cannot propagate. Or without water, water waves cannot propagate. So without some medium, light cannot also propagate, because light is also a wave. So just like how every other wave behave, this light wave should also behave like every other wave, having a medium. And they named it to be ether, luminiferous ether. That was the name given to the medium that they thought light should be in, and they started conducting experiments to find ether. Okay, so Michelson and Morley were setting up an experiment to detect ether, and they were very confident that they would find ether, and they spent 5 to 10 years refining their experiment, increasing the sensitivity of their experimental setup to detect ether. But at the end of it, they were not able to find ether, no matter how much they tried. So at the end of it, they were awarded the Nobel Prize for finding nothing. I mean, just a joke I normally make. It's not that they found nothing. They actually the evidence, there was no evidence for the existence of ether. So in science, finding something is as important or as important for the progression of science as to not finding something. Like if you found ether, if you then our understanding or course of action would have built important understanding of light. So we had to know what is the nature of light, whether light had medium or not. So light not having a medium, or light not requiring a medium to travel, was a very important understanding that scientists needed back then to understand further about light. Okay, so in that sense, the most famous experiment that found nothing was very important, and they were rightly awarded the Nobel Prize. Of course, Michelson and Morley, some of them were not convinced that light still, they still thought that ether has to be in. So they to be there despite the fact they were awarded the Nobel Prize for not finding it. So that's an interesting another story of entirely. But like I said, not finding something can be equally important, right? When I say not finding something is also as equally important as finding something. Now, this is a slide that talks about the importance of it. Okay, Albert Einstein. I'm sure all of you know of Albert. I mean, like he's one of those giants like Isaac Newton, who a lot of people look up to. The kind of contributions he made, like, is phenomenal. Like he's like looked up, like how people is looked up at. So now one of the things that he came up with is called special theory of relativity. I've put it as special theory of light. My mistake. It is special theory of relativity. Okay, so again, I'm not going to talk about what the special theory of relativity is and all. It's an entirely different session to talk about. But his entire special theory of relativity is pinned on, or rather, it comes from directly from the result of Michelson and Morley. So he assumed. So he until then scientists were confused about the nature of light, whether it has ether, whether the speed of light is constant in all directions. So Michelson and Morley's experiment once and for all settled the idea whether there is a medium for light or whether there is the speed of light changes in different directions depending on how we move towards it or away from it. So with that conclusive result, Albert Einstein was able to start his idea of special theory of relativity, because without that understanding, Albert Einstein wouldn't have started his special theory of relativity, the idea of special theory of relativity. That the very beginning of special theory of relativity is the idea of the result that came about with Michelson and Morley. When I say Michelson and Morley, not just Michelson and Morley, Maxwell's idea of electromagnetic light, of Michael Faraday, all the other scientists before Einstein, all their works culminated into an understanding of light that was required back then for Albert Einstein to propose his special theory of relativity. Okay, and what happened after that is an entirely different thing. But now here is the most important thing. Then my last but before slide. This is my last but before slide. Now, until that moment, everybody was thinking about light as a wave. It was almost conclusively established that light behaved like a wave. Okay, but Einstein was like, guys, wait, not so soon. Let's wait. Let's not like jump to conclusions very soon. Then he came up. He discovered a very new effect called as the photoelectric effect. Okay, I'm definitely not going to talk about what is photoelectric effect right now, because it takes a lot of time to explain it and some other basic understanding. But with this understanding of photoelectric effect, he again proposed, look, light does not just behave like a wave. Light also behaves like a particle. Light also behaves like a particle. He was like, look, light behaves both as particle and wave. It was like the most confusing thing back then. Even today it's confusing. But Albert Einstein was like, but to explain my photoelectric effect, you cannot explain the photoelectric effect if you think of light as waves. Look, his contention was that the photoelectric effect can be explained only if you think of light as a particle. The moment you think of light as a wave, this effect cannot be explained at all. So what do you want me to do? It is particle then. So now, in fact, Albert Einstein, for so many like he has come up with so many other aspects, like special theory of relativity, general theory of relativity, for all the things. He was awarded the Nobel Prize for this photoelectric effect. So we all know Albert Einstein was awarded the Nobel Prize in 1921 or 1922. I'm sure it's one of these 2 years. He was awarded the Nobel Prize for his photoelectric effect, for saying that light is also made up of light also behaves like a particle. So now we have come back to square one. But I wouldn't call it square one. That's just grossly unfair to say we have come back to square one. What I meant to say was we have come back to the idea of thinking of light as a particle as well. So because remember, way back in 500 BC or 300, 200 BC, people thought of it to be particles. But only that they just guessed it. It was not a proven, or it was just an insight. But right now we have conclusive evidence where through photoelectric effect, light also behaves like a particle. And the conclusive evidence for light being a wave is the Young's double slit experiment. Remember? So we have two experiments giving conclusive evidences that light behaves like a particle sometimes, light behaves like a wave sometimes. Okay? And do you? I'm going to ask this question to you guys. So do you know what was the name that Albert Einstein gave to these particles of light? I'm sure all of you know of this, the name given by Einstein, coined in that time, given to these particles of light. Do you guys remember? Can you type it out? Photons, correct. So Einstein is credited. So Einstein was the guy who coined that, I mean, who came up with this, the concept of photons. You know, light is made up of particles called photons. And I'm sure it is evident from the photoelectric effect, the name, photoelectric effect. Okay, photons. Photons are being emitted because of current. To give you a rough idea of what is a photoelectric effect, by passing current or because of electricity, or photons can be generated, or photons can generate electricity. You can think of it there. Light falling onto an object can generate electricity. Okay, photons falling to create electrical effect, photoelectric effect. Okay, so that was the idea, and that comes to the last slide of the session today. Right now, our understanding of light is that it is dual nature. So light behaves like particle to explain. So you'll have to think of light as a particle to explain certain phenomenon that you observe. You'll have to think of light as wave to explain some other aspects of phenomenon that happens because of light. So again, I've skipped a lot of other scientists who put in their tireless, efforts and work, years and years of work to improve our understanding of light. So the point is this: today, when you look at the book and you learn about photons or photoelectric effect, or you learn that light is a particle or a wave, you learn about light being a transverse waves where it goes up and down to the direction of propagation of the wave, or you learn that light does not require a medium to travel, only sound requires a medium, or light travels in a straight line, or light bends in a medium, or the Snell's law. Whatever you learn about light, what you're not learning or what you're completely opaque to is the fact that what went behind the scenes, or what went in the several thousand years that people have put their effort. And trust me, when I say people have put their minds scientifically observing things, it was not without any resistance. People with conventional belief systems, people with conventional religious scriptures were always been hurdled to understand or the progress of science. It is breaking the barriers, breaking the conventional like status quo, breaking, like, I will question. I want to understand the nature as it is, not as what the scriptures. I will not buy anything what I say. I want to do an experiment. Experiment is the only thing that can tell something is a fact or not what I believe. So the science has struggled a lot away. Today we are in a better position, definitely, because science has got more freedom to progress. Everything around you, right from this laptop that you're looking at or the mobile phone you're looking at, is emitting light. It has got LED screen. It has got LED, small LEDs that is emitting light. How are we able to create these things? It starts from way back. The simple understanding of what is light, that question has enabled all the luxury that we see around us today. And if it is not just for light, everything around you that you think, it has been brought to you by science. Every understanding about nature or science, whatever you do, it is because of science. And this is one story that has similar examples in all the other aspects. You can talk about story of gravity, you can talk about story of flight, how flights were. Once upon a time, humans would not have thought that people could fly, but today we are flying, not just within the world, we are going flying out of the world. We're going to Mars or going beyond it. Once upon a time, it was like not even possible. Okay, so now science breaks our mind free of the clutches or grips of what we're held back by our belief systems. So this is what I wanted to tell you guys. I hope you found this interesting, and I hope you learned a lot about the history of story of light. And right now I can take some questions for the next 15 minutes, and we will end the session by 8:15. I'm open to questions. Yes, I'm done for my session, Kavya. I'm done. I can take questions now. Yeah.
Thank you, Obliana, for this session. We are now open to questions. Can you please type in the chat box if you have any questions?
Yes, you can type in the questions. No questions? For so much about talking about questioning.